Welcome to session 2 of Python and Research Tutorial Series. My name is Jamaica Marshall, and I am a member of the CREST Creating Equity in STEAM team. Hopefully, some of you are returning from yesterday, and if so, then you know that we're going to be starting with Notebook 3 today. We have 4 notebooks to get through, so that means we'll be going at a quicker pace today. As a reminder, and if you weren't with us yesterday, I will share that we encourage you, we encourage you to post your questions about the tutorial, any issues or coding questions that you have. We encourage you to post that in our Slack channel. And so I'm going to post that link right now in the Zoom chat. Please click on that link and join the PyaR general channel, and that's where we'll have a Pardito. He was here yesterday leading one of the sections, so he'll be able to help you and answer questions in the Slack channel chat, as well as Geronimo a little bit later. The Slack channel is preferred because your questions can stay there. They don't disappear once we finish our session, and it allows the mentors to engage with you and others to contribute as well. All right. Any questions you have or any comments you have about the audio or the visuals when our mentors are sharing their screens, please put those in the Zoom chat though, so that we can address it right away. Okay, let's have a quick introduction. Let's start with Madeline, then Artem, and we'll finish with Geronimo, who will then take us into Notebook 3. Welcome, Madeline.
Hi, everyone. Can everyone hear my mic? Awesome. I'm a fifth-year graduate student, means I'm working towards my PhD in astronomy at UCSC, University of California, Santa Cruz, and I study exoplanets, which are planets around other stars, and I make computer models of them.
Wonderful. Thank you, Madeline. Artem, welcome.
Hi everyone, welcome back to PyaR. My name is Artem. I'm also from UCSC, so University of California, Santa Cruz, just like Madeline. And yes, I study planets, and I'm very interested in their composition. And to do that, I use a lot of programming, and that involves daily use of Python.
Fabulous, Artem. Thank you. Geronimo, welcome.
Thank you so much. Hi, everyone. My name is Jerónimo. I am a Colombian master's student currently in the University Côte d'Azur in France. I'm doing my master's in astrophysics. And as Artem and Madeline were mentioning, yeah, it's always in every stage of our formation as astronomers, as astrophysicists, it's always a very important tool to have programming languages handy, and Python is one of the most widespread ones that we will use. So yeah, I think I've been using it for a while. I'm very used to it. So it's it's very cool to share a little bit of that experience from all of our different levels of formation. Very glad to be here.
Thank you so much, Madeline, Artem, and Geronimo. Okay, so we're going to be jumping into Notebook 3, led by Geronimo. We'll be keeping a pretty quick pace. So we do welcome your questions, again, in the Slack channel. Any questions you have about the coding process, any of those components, any issues that you're having, please have them in the Slack channel. General questions about audio or visual things or any links, for example, those can go in the Zoom chat. All right, let's head over to Geronimo, who's already ready with Notebook 3. Geronimo.
Okay, perfect. So just as a very quick context recap from where we arrived yesterday, we managed to explore a little bit the like a first view of the different tools, the different capabilities that we have, both with the Python programming language, but also with the Jupyter environment notebooks. That is very comfortable, very useful for running different scripts, but also like running different tests. It can be used also as a little scientific calculator, so doing quick calculations. that we may need, that we may have to keep handy sometimes when we are trying to do some scientific activity. So it is very useful to have it. So now we're going to start with something that is trying to construct a color magnitude diagram. Like yesterday on the little part of astrophysical context that we gave of astrophysical like concepts that we need to keep in our mind. We spoke a little bit about color, which is we will calculate it later, but it's defined as the difference of brightness that we measure on a source, on a star, for example, in two different filters or two different wavelength bandwidths that we use. And this is very important because the cameras we use to capture the images from stars can really see in very specific color windows. So it's there's a lot of information kind of hidden or kind of waiting to be unveiled from the images we take in each of those color windows. So if we subtract two of them, the intensity that we measure in two of them, this may give us a lot of information about the star that we are observing. In this case, we're going to use some observations taken under a survey called SPLASH, and it's a bunch of observations from the Andromeda Galaxy. So it's stars that are part of the Andromeda Galaxy, and we can have a lot of measurements, very useful measurements about those stars that can tell us stuff about the individual stars, but also about the whole galaxy, the Andromeda Galaxy as a whole. So that's also very interesting. First, as in any notebook, as in any Jupyter notebook environment, we start by importing the necessary libraries. So we run this first cell. Here I get some warnings, internal details that the program will give me. But in general, remember, we're using this NumPy package that is very useful for handling arrays of values, which is the objective today. We're going to analyze data that is stored in long lists of values, but in this case, we call those lists arrays because they have some specific properties that differentiate them from the normal lists that we saw yesterday. We also import this library matplotlib that is very useful. It will allow us to display that information in a way that looks nice, that is pretty and also very clear. And then we're running this little magic command that, if you remember, it's just a command that tells the environment to behave in a specific way. In most cases, we add this so we avoid it opening different windows or different tabs. It just does everything within the same tab that we will. For this specific one, due to some functions that we're going to define, we also call the general, we invoke the general matplotlib library as a deal, but you'll see why. Straightforward. Here, I think this is a notebook that was designed originally by our friend Philip, who in this version I think is not with us. But he would put together this amazing set of notebooks, and he defines here a very specific set for the appearance. So he says he wants like a font of like a specific font for the text that is going to show on our plots, and a specific text size, which is going to be 14. And that's why he used this PL library, so he can run that very easily. So that's not very necessary. Like that's just a matter of taste, but we have it anyways. Then we're going to have a small function that will initialize our plots. So it's also an aesthetic function. It's not completely crucial for the functioning of the activity. But in this case, in this notebook that we're using, and even if you want to use it for exploring Python a little bit more on your own projects and doing other plots, this is a very useful function because whenever you run it, it really sets up the appearance of your plots. So if you know what you're plotting, you know the range of values within the X, Y axis that you want to display. And you have several plots that are going to have the same information, are going to have some values on the x-axis, some values on the y-axis, and they're the same quantity, so you want to write the same labels. You can use a function like this, and it's very useful. So, this is why we have all this in the start. Usually at the start of our notebooks or the start of our scripts, we have all this setting up that is useful because you can put there everything that's going to be useful for the functions below that are going to be the actual data analysis. analysis and the actual data visualization. Here we have also a specific function that is going to be also useful to take data from a catalog that we're going to be referencing, that we're going to be using. So all the data we're going to be analyzing, we're not going to take it. We're not going to go and point a telescope towards Andromeda and take all the information from all of these stars and save it in a table. Because if every astronomer had to do that over and over again, it would be very inefficient, very expensive. Instead, we have very, very amazing databases that store all these amazing catalogs, all these wonderful sets of huge amounts of data that just hold everything in the same place, and we can refer to them and just download little text files that have all the information we need. So in this case, we're going to have this function that if we give it the catalog, and we insert some specific parameters, like we select with some specific conditions, it will select only a little chunk of the whole data set and save it as a different catalog. That's going to be useful later. We're going to see why. It's not that necessary to go into detail of what's happening within this function. It's just going to be useful because we need this data set or this other selected catalogs for the following activities for the other nodes. So this is also useful function that we're simply going to use. It's very normal also when you're programming that sometimes you're using functions that are very, very sophisticated, that are very complicated, that you don't know actually how to program, but they do something you need or something that makes your life much easier when programming. So it's very normal to have functions like this sometimes that you find in the internet, or some colleague can give you the code, and it does something very specific that allows you to run the rest of your code in a more comfortable way. Okay, so now that we have the packages and we have all the functions, we can start by doing or trying to do the scientific activity, which is really fun. So the first thing is that if you downloaded the notebooks, the empty notebooks, you'll see that in this SIP Python workshop folder, the notebooks are stored in this folder programs, but also there's another folder called data. And in that one, there is this file called kehstdata.txt. If we display that, the cool thing also I really like about Jupyter, the Jupyter environment, is that it allows us to display many different types of files, not only notes. You can also display a terminal, you can also display scripts, text files. So it allows you to really, really inspect what you're working with. So here we have two first lines that are commented. Remember that this hashtag means that this first line is going to be ignored by the code. It's just information that is useful for us as the users. So it just tells us what is going to be in each column of this data set. And it's just giving us an extra information that is that all the coordinates are in degrees. What do we have here? We have positions in the sky of each star in the splash survey in this on the Andromeda galaxy that will be denoted with these two numbers that are the right ascension, so it's RA, and also the declination, DEC, dec. So these are two angles we use to find points on the sky. So they're useful for finding points on a sphere, similarly to how on Earth we use the latitude and the longitude to give the coordinates of a place on Earth. Similarly, we have some coordinates to give the position of stars in the sky, and those are usually the two angles of the right ascension and declination. Also, for more specific like location, or like within the context of our problem, which is stars that are in the galaxy of Andromeda, there's also these coordinates. So you can locate these stars with these two numbers, with the right ascension or the declination, but also you can use chi or eta, which are the two angles which allow you to find things with respect to the center of the Andromeda galaxy. So if you see the Andromeda galaxy in the sky, the center is going to be 0 in chi, 0 in eta, and then these other stars are going to be an amount of degrees to the north or to the east of the center. So then we can use this third and fourth columns of this data set to quantify that position with this other two coordinates. So it's just a different way to locate the stars of the data set with coordinates that are with respect to the center of the dot. Then we have these two weird sequence of letters and numbers. Don't get too scared or too confused by that. These are just the names of two filters. So it's like pretty much telling the camera of the telescope to look at two different colors. And one of them is going to be at a wavelength of 475. I would say this is nanometers. Correct me if I'm wrong, but I think if it's Hubble filters, they should be 475 nanometers. And you have 814 nanometers for the other one. And these are just the way we quantify specifically around which colors we're looking at. So yeah, we could say this is like a very short wavelength, but still, if I'm correct, yeah, within the visible regime, within the optical regime. So we could say this is kind of bluish colors, maybe even green even. Yeah, because 500 will be green. And then you have something that is beyond 700. So this is pretty much infrared, like near infrared. So we have something in the near infrared filter, and then something that is going to be in the kind of greenish, like part of the spectrum. And then we also have a couple of columns that will give us information on the velocity, because these stars moving way or closer to us. And there is a very, very nice technique that astronomers use to try to measure this movement. So how fast stars are moving towards or away from us. So this is also another column that we're going to be using, and you'll see that these numbers are here. And in the last column, it just gives us like an idea of the error, or like how accurate these measurements are. So this is always very useful. So, okay, this is the document we're going to be, or the file we're going to be working with. As I said earlier, we're not going to go and take all of these measurements again, because very, very capable astronomers, very smart people with amazing instruments. I understand this is both from the Keck Observatory in Hawaii, and also the Hubble Space Telescope, which is at the lower Earth orbit around the Earth. Have gathered this information for us, and now we can all use it to learn something new about the Andromeda Galaxy through it. So we can simply run something very cool, which is NumPy has this very cool function called load.txt. So we have that txt file, which is saved, that is the name of the txt file, and it's saved in the data folder. So we have to tell the Python code that is like, okay, when I write these two dots, it's telling it, okay, you're within a folder, go back once, because you remember we have to access the data from the programs folder. So to tell, so anything we write or we try to look for with the function load.txt is going to look for files that are here, unless we write that little dot dot. When you write dot dot, it's telling the notebook or the Python script to go back once in the folders, and then when it goes back, it accesses the data folder. So it says data right here. So if we check, we go into data, and then there it can find then the right file that we're looking for. Then we write the name of our file, and then we can, since we are loading several columns of data, we can straight away just tell it, okay, save each of those columns as a different variable, or as a different array. So we're going to have the right ascension array, the declination array, the psi array, eta, the two filters, F475W and F814W. Then we have the velocity and the error, the radial velocity. So we can straight away just tell NumPy, okay, assign all of those. Remember that the equal sign here means assign it, like just save all that information in different things. So we can save it straight away in all of these arrays. And then we define the color, which is the color index we were mentioning yesterday, simply as the difference between how bright the stars are in these two filters. So we have the brightness in each of the colors for all of these stars. And since they're different stars, they don't have to, there is no reason why they would be equally as bright in both filters. They will necessarily be, there will be necessarily a variety of stars. They will have, some of them will be redder, some of them will be bluer. So this is going to translate into different colorings. And this is how we quantify color in astronomy, and is what we're mentioning here. So if we run this little cell, now we can count on our Python code on having saved in each of these arrays the information we need for developing this activity, which is going to be plotting what we call a color magnitude diagram. So a color magnitude diagram is very straightforward. If you already define this color quantity, what you want to visualize is displaying on the x-axis that color quantity, and on the y-axis you choose one of the magnitudes that you want to display. And this sounds kind of simple. It sounds a bit random, even like why these two quantities. But very early in the astronomy of the 20th century, astronomers found out that if they try to visualize this, they can divide different populations of stars. So you can tell that there is like little star families that have different characteristics, but they can be grouped in like different types. So today we're going to try to identify 3 of those types, and we can start by visualizing that. So we can run our little function initialize plot, which is just to make the code more compact. So this is telling, okay, run matplotlib and like design a figure that has some specific shape with some specific font. So that's you can check it again on the beginning of the notebook if you maybe lost the plot on what this little function does, but it's just setting up the plot for us so it looks nice. And then we can tell we can call the matplotlib module that scatters points. So we have 2 arrays, the color array and the 814 filter array, so the brightness, pretty much the magnitude. And these 2 arrays have the same amount of elements. So we're telling matplotlib to take the first element of the color array and match it with the first element of the magnitude array, and then put them together in the right? And it goes point by point, plotting all of them together. Here we're defining, okay, do it with the gray color. So just plot a ton of gray dots with a size of 3. You can change this if you think it would look better with a different color, with a different point size. And here we add this edge colors parameter. But all of this is aesthetics. The main part is this first line right here. The rest is just how we want it to look. But the important part is going to be done by just running scatter with the X values and Y values. And here we should get a little color magnitude diagram, which should be nice. So you can zoom out a little bit if you want to get in better in a single view. So it looks like this. So here you can see how the magnitude, this is very important. The magnitude values, remember that the lower they are, so look that as we go up, they get smaller. That means that those are bright stars. So magnitudes are an inverse scale. So if it's a smaller number, it's a brighter star. So you can imagine that the ones that are here on top, that it's like a very sparse field, it's not many dots over there. They're very, very bright stars. And then if you go down here, like around 24, there's also not that many, but those are the faintest stars of this field. And we see that they are like clustering in like groups right here around the 21 magnitudes range, but also in different values of the color index. So that's also interesting. And the point is, we're noticing, we can start to notice that there's like 3 big groups right here. We see that there's like one here to the left and goes all the way from the bottom to the top. Then we have like a big blob here in the middle. And then we have like some other population here to the upper right. So we're gonna try to find those and like set a characteristic that separates them as like star families or star populations. So we can start by analyzing that. So I'm gonna zoom in that a little bit. And so yeah, so we have this CMD, color magnitude diagram. And we want to separate out the stars of these 3 different types that we're mentioning. And now we're going to start naming them. So the first group we're going to try to identify is what we call the main sequence star. The main sequence stars is what usually we can refer to as a star in its like normal adult life. So stars are born, and when they are born, they can be very active, a bit rebellious, we would say, if you put a parallel with like human lives. And then they settle, and they, for a while, they settle down, and they become like very, you know how they behave, that they have like very understandable behavior, I guess, and is what we call the maturity of a star, and it's usually called the main sequence, what we in astronomy call the main. But there's also other stages after the main sequence. And this is where we start talking about the red giant branch and the asymptotic giant branch. So what happens is that stars start expanding and they become giants. It depends a lot on the initial mass of the stars. But the ones that we're going to focus on here are stars that after finishing their main sequence life, you can see this as they are stars that are retiring. They become giants, they start expanding a lot, they become some of these like turn to the more red side of the diagram. Because also another thing with the color, remember that um, if the color value is higher, so the color values more to the right are redder stars, and then the color values to the left are bluer stars. So we're going to try to identify that, just to give a little tiny spoiler, that this population here to the left corresponds to the main sequence ones. And then here, these two will correspond to the red giant branch and to the asymptotic giant branch, who are the redder side of this field of stars that we're analyzing. So we're gonna try to identify those and try to select them and save them in some new catalog. So we're gonna like take slices of the original catalog we have and save them in 3 different catalogs that are gonna host our main sequence, like a list of main sequence stars in this set, RGB stars and AGB stars. So that's the main objective that we're gonna try to do. So here for that, we can start by defining, okay, from what it looks in this plot, we could see like there's like a division in color here between the main sequence ones here. So we could say that, okay, the criterion to select our main sequence stars could be just saying, okay, there could be a maximum value of the color index that we can choose and just take from below that, not taking up to that. That's going to be main sequence, and beyond that is not going to be main sequence. So that's what we're doing here. We're going to say, okay, main sequence is going to be wherever, and remember that Python is very, very useful kinds of things for defining conditions. So this is going to save where this is going to save as true or false of where these color values are lesser or greater than 1.75. So if it's lesser, it's going to be true. If it's higher, it's going to be false. And we're going to add here an AND statement that is going to also impose the condition. Okay, we also want the magnitude to not be very high. So we're going to also impose that, okay, it's going to be from 23 upwards. If we run those two, we can already identify, okay, so select these MS values, and then what we plot is the whole set of values that we already plotted, the whole set of data points from the table. But now we can also plot by adding this little square bracket with the MS condition that we added. So we make sure that it belongs to the main sequence. And on top of the original data set, we plot only the main sequence selection. And we can do it by changing the color. For example, we can just plot it on blue and make maybe bigger points, and that's going to be more noticeable. And we can also add with this function plt.text, we can write whatever text we want. In this case, we're going to add text ms, so we can visualize and identify that what we are plotting on top of the original field of stars is the main sequence ones that we are identifying. And we can give it the coordinates. This is going to be very arbitrary. We can choose depending on what looks better within the plot. But we can change this. You can just play around with these numbers to see what the labels show up and until you are satisfied. So if we do that, we run it, and we're having now this plot that shows all the stars from the data set, but also it's on top of that selecting the slice of stars that we are with our criterion that we imposed, that we consider are from the main sequence. And we have this little label, this little text tag that we decided to put there that says MS to identify as main sequence. So now We can do the same for the others. You will see that if you were running this notebook, or if you try to run it later, you'll see that, okay, you can also we have some comments here that tell us, okay, you can also do that for the RGB stars, for the AGB stars. Since we don't have too much time, I will do it right now, and I have a solved version of the notebook, so I will just copy some of those commands from that one. So what we have to define here is, if you see, we can uncomment this RGB line. So it's going to be, okay, we want it to be higher, because for the main sequence, it was lower than 1.75 in color. So we can identify like this little division between the two populations. So we can say, okay, lower from that is going to be main sequence. So upper from that is going to be no longer main sequence. So we can start by imposing that condition to say that those are going to be RGB. But then if you notice, there is the division between the other two populations, between the RGB and the AGB, is not that clear. It's not just setting like a straight line. Here we're going to choose, and this is very important in the scientific thinking, you can choose different models that you're going to impose to make your selection. So here we can say, okay, this kind of looks like a parabola, you know, like this little curve that separates this blob right here from the rest of the AGBs that are going to be more upwards. So we can try to slice it using a parabola, because a right line is going to be maybe too, I don't know, too rough around the edges. We want something that is a bit more curvy, so a parabola might work. Maybe if you also do a different model, I don't know, if you have a more complicated function that you can use to impose this condition, maybe it will work better. But sometimes there's simple solutions like running a parabola that would work. So we can define this parabola by setting up a position of its vertice, and by defining that position and defining how curvy the parabola is, or how much curvature it has, we can define like a boundary between the two regions. So this is what this little commented text was telling us. You can define that the y values, which are the magnitude values, have to be higher than some parabola equation, which is defined as this. So the only thing we have to do is set values for a. Let's see. Not used to this keyboard, I'm sorry. But I have the code right here.
Geronimo, just a reminder, we're at 10 minutes left for this section.
Perfect. Okay.
Thank you.
Yeah, I think we'll be able to make it. So I have saved some values that I know that work pretty well for defining this difference between the two. So I'm going to define this. A can be around 0.1. You can also play around and see if you get something that looks better. It's also perfect. This is something that we're just using by eye right here. And as I was saying, that's part of the scientific thinking. You want to run different models. You want to try different things and compare different results. Don't just stick to the first result you got and think that that's the best. You have to try many different ones, and that's going to be the way to proceed. So you can choose an optimal one from a different selection. So here we can choose those, and also we can, I will copy this part of the commands that just runs just adds to the plot the RGB ones. So I'm just doing it here very quickly, but it's exactly the same as we ran for the MS one. So it's running the same command of the scattering the plot, but we're choosing, instead of the MS, we're here running RGB, because we already imposed a condition for the RGB stars. And I'm gonna just change the color of those points. They're gonna be red. And I'm gonna write a little label, plt.text label, that is gonna indicate me, okay, now these ones that I added are gonna be the RGB ones. And then I'm going to write into the catalog with this little function that we were mentioning earlier, similarly to this one. I just copied that one and changed where it says MS, I changed for RGB. So it saves the values of each of the parameters into the RGB catalog. So notice how I'm creating here this ms catalog.txt file, which is going to be useful later. And now here I'm changing that for a new catalog that's going to be the RGB catalog.txt. So that's going to be useful because now I'm going to have separate text files that are going to host the segments of the table that have the information I need, the specific stars that have the information that I need. So I know that, okay, the ones that are in this catalog are main sequence, the ones that are on the other catalog RGB. We could have run this and see if it works. So as you can see, here's clearly is our parabolic like boundary between populations, and this is going to be the RGB set of stars. Very similarly, now it's pretty much repeating the same process, but be careful that now that we're going to do it with the AGB, I'm going to copy very similar. It's just the same commands, but changing the labels to AGB, and it's going to work. But be very careful because for the RGB, we want to make sure that the magnitude value is higher than the parabola. So it's like higher, it's going upper than here. So yeah, remember that the scale is inverted. So higher is going to be downwards here. So higher values, higher numbers are going to be downwards in our y-axis. So they're going to be higher than the parabola that we defined. And now we're going to have to flip it and make it lower. So notice that when I define the condition for the AGB ones, they have to be lower than the parabola, but it's the same parabola that I just defined. Just that, as I said, I may repeat a little bit, but it's just that repetition is important. Clear. RGB are going to be higher than the parabola, AGB are going to be lower than the parabola, but it's the same parabola for both. So it's just changing that, and then I'll change the AGB condition into the same lines of code that I just did. I'm going to do the scatter function, so we get the plot, but I'm plotting now the color and the magnitude within the AGB condition, and we can define the color to be different. Now, in this case, I chose green. You can choose whatever colors you prefer. And now I'm gonna add a little text label that, again, you can play around with the coordinates for your text. This is just aesthetics, so as you prefer, but it's important that I'm putting here the AGB label so I know which of these populations is which. And then I'm generating with the right catalog function, I am generating the AGB catalog.txt within the data folder. And I'm just replacing in all of these columns, I'm replacing the columns that have the condition of having the AGB as a true statement. So that is very important. So now we're going to, after running this, after completing this, try it on your own. If maybe something doesn't work, just text me on the Slack. We're going to be trying to help each other out over there. And yeah, so one of us is going to reply to some of the questions. We're going to be online to help you out if there is something that's not quite clear or not working exactly well. So yeah, but after running this different commands for the main sequence, the RGB and the AGB, we can run again this cell. This is also another very cool thing about the Python notebooks. It's like you can run a cell again and again and change things and run it again, and it lets you test things while you're changing them on the run. So it's very useful. Now we have this beautiful plot that now has all the populations that we identify. So we identified the main sequence as something that is before some specific color value. We define it as 1.75, I think. So before 1.75 in color, we identify those as main sequence. After 1.75, we have the RGB and the AGB, which are divided then by the parabola boundary that we define. So that could be a little bit tricky to wrap your head around, but don't hesitate to ask us again in the Slack channel. We're going to be right there to reply some of your questions. So yeah, now we have identified the main sequence, the AGB and the RGB stars within this data set that we're working. And here there's a couple of lines of code that should be also in the other notebooks that just tell us the proportion of the total stars that are main sequence. So it's around 15% of the stars in this data set are main sequence. The RGBs that are 54%, the AGBs that are 14%, and some of them maybe were not selected because not all of them fit the parameters that or the conditions that we were imposing. So 16% of them apparently didn't fit those conditions. So this is also an important step to visualize, like to quantify, okay, what is the demographics of stars within this galaxy, right? So like how can we identify which one is more common? Why maybe these RGB stars are so common? It's one of the questions that we can start asking ourselves as we dive into these stellar astrophysics topics. That is always very interesting. So yeah, I think that's it for running this notebook. I don't know if there's any question that we can address directly, or we can move ahead with the next part.
Geronimo, thank you so much. Yes, there is a question over in the Slack channel from Joseph. So whenever you or Artem or Aparajito or Madeline can jump in and answer that, that would be helpful. We so appreciate it. He's talking about his RGB graph isn't quite right. So
Okay. Oh yeah, yeah. I'm just checking here. Okay, I think we can discuss the possible solution and read a little bit the code in the Slack channel directly and try to
amazing.
help him get it right.
Thank you so much, Geronimo. Okay, now we are ready for our next session, and this is going to be presented by the fabulous Madeline. So Madeline is going to give us a little bit of astrophysics background and then lead us into our next notebook, which is notebook number 4. Madeline, welcome. Oh, you're muted. No
I
problem.
hid my floating meeting panels too quickly. Okay. All right, so as long as everyone's hearing me, we're going to keep moving quickly, quite literally, because we're going to be talking about the Doppler effect. So the Doppler effect is something we have actually all heard in our daily lives. This is when you hear a siren going by, and you notice that as it approaches you, it starts to get higher in pitch. Something like... We might recognize that sound from motorcycles as well as they pass us. And that increase in pitch as it approaches us comes from the sound waves, in this case, being bunched up as the object is moving forward, causing it to be higher frequency. So bunched up sound waves means shorter wavelength here, and it also means a higher frequency. And on the back end, because the sound waves are being stretched out, we have a longer wavelength and a lower frequency of sound. And the same thing actually happens for light waves. Light is wave just like sound. And so indeed, as we have, for example, a star moving away from us, remember this diagram, how when it's moving away from the person, these peaks of our wavelengths get stretched out? Well, indeed, the same thing happens with wavelengths of light. And when a wavelength of light is longer, it's redder. On our rainbow, red is the longest wavelength, and blue or violet is our shortest wavelength. And then, of course, it goes on into things we can't see. They're so short, like ultraviolet and even shorter X-rays. But we call this red shift because it's stretching out the wavelength of light. And we call this blue shift because it's compressing or shortening those wavelengths of light and making it appear bluer when it reaches our eyes. So there's a couple of types of redshift. In particular, the one that we are going to be talking about, because we're thinking about our nearby neighbor Andromeda, is going to be due to the relative motion of galaxies relative to one another. Because Andromeda is approaching us, just like the ambulance in this example. Okay. In the ambulance in this example, we are going to get a blue shift, potentially, from Andromeda. And the other types of redshift we may see when we think about astronomy, one is due to the expansion of space between two stationary objects. And this is because our universe is actually expanding right underneath us at this moment. And so as the space stretches between us and our nearest neighbors, we're going to see some redshift. However, the reason we don't see that with Andromeda is because gravity is still stronger than the expansion of space underneath us. The classic example people give to describe universal redshift or the universal expansion is imagining drawing 2 points on the surface of a balloon, and as we blow up that balloon, those 2 points spread away from each other equally in every direction. Though we don't worry about that with Andromeda, again, because the pull of gravity between the Milky Way and Andromeda is still stronger than that force pushing them apart. And type 3 redshift is, if you're sending light around a black hole, it can be warped by gravity or any sort of thing that will warp it, called gravitational lensing, and that gives us a small form of redshift. So because we use redshift to determine how fast something is going, and because we know that the universe itself is expanding, we can actually correlate the two to determine distances. So if something is on the surface of our balloon further away, it'll actually be moving faster because it's more distant from us. And so we can use that information about how much it's redshifted, the light coming from it, to get a distance of how far away it is. In general, we don't tend to think of spectra or rainbows, different wavelengths of light coming from an astronomical object in this sort of rainbow form. But this is a really helpful way to sort of picture what redshift on a spectrum looks like. So when we talk about spectra, what we mean is different wavelengths of light, the amount of different wavelengths of light that are coming from an object. And so we can kind of picture that as a rainbow when we think about, okay, maybe there's a lot of purple coming from this object, but oh, something is absorbing this particular wavelength of light, so it's not reaching us. And using these features, we can line up what our expectation of the spectrum would be with what it actually is, and then calculate the difference in the wavelengths. So if we were standing right next to the star, what we would see is this perfect spectrum right here. We back up to our actual distance and we notice, oh, hey, interesting. These lines are not where we expect them. There is, in fact, a difference in the wavelength of, take, for example, this line. And the reason that is because the light is being redshifted on its way to us, meaning the object is moving away from us. What this really looks like is something like this. This very pixelated example is a more realistic version of a spectrum where we measure the amount here on the y-axis of each wavelength, here on the x-axis, of light that's coming to us. And here are those same sort of absorption lines, the same black lines we saw on the last slide, but now it just shows up as there's less light coming in at that wavelength. So if we were to look at the spectrum of a moving star, and let's choose this particular absorption line. We're going to see if we can match that up. This is what we would see if it was moving. Sorry, green. This is our rest. This is imagining we were standing right next to the star. This is what we should see. But indeed, when we observe it, we notice, oh, okay, from our distance, we can see that the spectrum is shifted over. If we look at this line here, this absorption line, we notice that it is shifted over from what we think the ground truth should be. And so using that difference in the wavelengths, we are able to calculate the velocity it's moving. Now we use this formula for Doppler shift or velocity redshift, using this difference between our rest wavelength, the wavelength that we would assume if we were standing right next to the star or the galaxy, and what we observe here on Earth, to calculate velocity, where velocity is our v value here. And in particular, pay attention to this. When v is less than 0, it's moving towards us, and when v is greater than 0, it is moving away from us. That is just how we define it. If we defined it in the other direction, we would have to change some of the signs to minus signs. But to use this formula, we're going to know that velocity less than 0 moving towards us, velocity greater than 0, it's moving away from us. And c is our speed of light. And because we're working in units of kilometers per second, we know that the speed of light in kilometers per second is 3 times 10 to the 5, or 300,000 kilometers per second. So we're going to use this formula, 1 plus v over c, times our rest wavelength, to get our new wavelength. And we're going to migrate over. Is everyone still seeing my screen?
Yes.
Okay, thank you. We are going to, I'm going to zoom in a little bit so everyone doesn't have to zoom in on their own screens. Okay, so how do we apply that information? Well, we're going to be looking at the velocity or the redshift of Andromeda. So, as always, we're loading in the libraries that we're going to use, NumPy, Matplotlib. We've done this a couple times, so we're going to move past it. So now we're going to do something called defining a function. In particular, we're going to define a function that can take our rest lambda and turn it into a new lambda. Now, if we remember, we know the equation for that. Let's go back to that slide to see it one more time. It's 1 plus v over c times our rest wavelength is going to give us our new wavelength. So that's our rest lambda, 1 plus v divided by c times our rest lambda. Now I'll pause here for a second. Make a prediction just to yourself. What's going to happen when I run this? Have I defined all of the values in this function? The way I define the values in the function is by having what are called arguments. So using this structure, I have a function called shift to moving, and these values in here are arguments. These are something where I will get to input the value and then get an output. And the output is this value new lambda. So I have an input of rest lambda. I have an input of v. Yeah, we don't have an input of c. So I'm actually going to just go ahead and define c, since we know c is a constant. I'm going to write it in the scientific notation way that we use in computing, which is using e and 5. Don't do any spaces or it becomes something else. So this is equivalent to 3 times 10 to the 5. The other way we could write this would be 3 times 10, double star for our power, times 10 to the 5. Okay, so in order for this to be a usable function, we have to execute that cell. All right, so to give us an idea of what we're going to be doing, I'm just going to point to this line up here that says we have spectra from some stars in Andromeda. These stars have numbers for names, because that's how we do it in science. We don't give them actual names. Because there's simply too many stars to name them all. And we're going to be finding the radial velocities of those stars. So using this function, let's put it to the test. So how we would test this function is by calling the function. I'm going to type shift to, and then I hit tab, and tab auto completes the function because there's only one other option it could be. I just hit tab and it fills in shift to moving. Now imagine, actually this is a trick. Imagine I didn't remember what this was supposed to do. I'm like, oh yeah, what are the arguments that are supposed to be in shift to moving? A trick you can use is to hit shift tab, oop, and look at this little informative box that shows up. I can click on it and I can learn a little bit more about this function. I see that the thing that was highlighted with 3 quotation marks and closed by 3 quotation marks is actually a description called a docustring that tells me what it does. It says function to shift a wavelength array using Doppler equation. Cool. And I can see that my arguments are rest lambda and v. So we know that our rest lambda value is this rest H alpha. That's one absorption line called hydrogen alpha. So I'm going to do rest H alpha. And then we know that our V equals, well, we're going to see. We're going to test some values. Raja asked us to test 200 kilometers per second. So let's just execute this and see what happens. Ooh, okay. So we see that we have a positive shift, that our new wavelength should be a little bit off. It should be 4, actually know the units of this. I guess kilometers off. Let's try it again. Actually, you know what, folks, just in the sake of moving on, I will ask you to practice formatting this in a print statement, because if we wanted to, for example, do this again, and we wanted to test it with negative 200, what would happen is, oh, I only get the output for the last line that I put in. I don't get the output for this as well. So if I wanted to, I have to put it in a print statement in order to get both. Or I can, call this a variable, maybe new lamb, and then use that to print, or put it as part of a print statement. The new wavelength is, and then using our variety of options for ways to print this, I can put %, and then this just means give me 2 points after the decimal, and then I put a %, and then I put new lamb, the name of my variable that I put my output to. So the output of this function is now in a variable called new lam. And so if I wanted to make this a more informative way to print this out, I'd say the new wavelength is this. So I spell wavelength correctly. Okay, so moving on, what we're going to do is we're going to choose one of those stars that in Andromeda that I said that we have spectra to. We're going to try to pick a template to see if it belongs to one of those populations, either main sequence, red giant branch, or asymptotic giant branch. These just allude to different phases in a star's evolutionary life, as we learned yesterday. Okay, so we're gonna fill in, we're gonna choose, I'm gonna be lazy, I'm gonna choose the first one. Okay, I've chosen the name of the star, and we'll again just be lazy and choose the first one. Okay. So what's going to happen when I execute this cell is I've named a variable star name, and this is the name of the star, and then I can append it to this string. I can stick it to the string by using plus signs when it's a string. If I were to use these plus signs and it was not a string, it was say a number or something else, a float, as we call it, it would not work. So this form only works when we have a string. So what this is doing is this is making an address where this data lives. And this is kind of neat because instead of having to type the whole thing over again every time, /data/ /spec.text, we can just use these variables and just change these variables and substitute it, and it will find the right location because this is just a location where the file lives. Okay, so then what we're doing is we're using NumPy's load text function. This is a native function of NumPy. Unlike the function we defined ourselves above, you can just call np.loadText. You can give it the file that it's going to load, the text file it's going to load, and then putting this argument unpack equals true is just unpacking the columns of that. You can actually go look at this location in your own time and see what those columns of data look like. And we're just going to unpack those columns, and we're going to put them into the two columns, put them into variables named psi lambda and psi flux. That's because the contents of these columns, remember what a spectrum looks like. A spectrum is our wavelength versus the amount of light at that wavelength, the flux. So we're getting our spectrum from these files. Execute that. Okay. Alrighty, so we are now given a pretty filled in form here. And what we're going to do with that is we're going to manipulate the independent variable, the velocity of our guess. So what is this? What are we trying to do here? Well, we're going to try to shift our template spectrum, which is this temp lambda. This is imagining we were standing right next to the star. This is where we know the spectrum should look something like this. And then the actual observed spectrum is this one called psi. And because they should be offset slightly because of the redshift, what we're going to see is that they don't line up if we let v equals 0. If we assume that our galaxy is not, or the star is not moving at all relative to us, we'll see that these are pretty badly misaligned. Huh? Well, actually, this is important. Notice how this is actually not the right shape of spectrum. That looks pretty darn different. If anything, this black one looks like the one that we chose for our presentation here. So that tells me one thing right away. That tells me I shouldn't try to match apples to oranges. In fact, I probably don't have the right template. So this is probably our red star here, our real life star that was observed in Andromeda is not a main sequence star. So we're going to go back here and we are going to load in a different template. We're going to see maybe it's an RGB star. Maybe that makes more sense. We're going to load this again. Okay, closer in shape, but still not quite. Maybe it's an AGB star, an asymptotic giant branch star. And so I'm reloading this. Notice how it's convenient that I can just change this variable name. I don't have to change the entire string that leads to the file. There we are. Okay, those look somewhat similar. Okay, but we still have an issue where they aren't perfectly aligned. So let's see what happens if we shift our template over using a guess at what the velocity of the star could be. Well, I know we've guessed 200, remembering that positive is moving away from us and negative is moving towards us. We've seen the number 200 kilometers per second a couple times, so I'm just going to make an educated guess, and maybe that's something. Okay, maybe, but kind of to the naked eye, it looks like I'm still a little bit off on these peaks and troughs. They don't quite line up. So I'm going to guess, okay, maybe what if it's negative 200? Okay, interesting. They do seem to be a little bit closer aligned, but it's kind of hard to tell just from this zoomed out view. So what we're going to do, and you can do this in the same cell, but I'm going to copy it over so we can see the difference. I'm going to add a new cell. I'm just copying the contents of this existing cell, and I'm just going to zoom in. This is in your instructions in this next paragraph. So we're recommended to set our zoom limits to that many angstroms. So I'm going to do AX. So on the same set of axes, set our X limits of our X axis, and we're going to zoom into 7,000 angstroms to 7,200 angstroms. What this is going to do is it's going to zoom in because it's limiting the X range that we're plotting. Maybe. Okay, cool. So this is way easier to try to shift over and align these guys by eye, you know? I thought I was doing pretty good up here, but as you can tell by looking at this one down here, we're actually still a tiny bit off. Now, I think I remember from having taught this class before that negative 250 is actually a pretty good guess. Okay, for the purposes of today, we're going to call that good enough. You can mess around with these values. A really important thing that we do in science is we really try to understand what the effect of changing independent variables is. And one way to do that is to make some pretty crazy and extreme guesses just to understand what happens when you change that number. So I'd encourage you to do things like put in 1,000 and see what happens. We already saw what happened when you put 0. Just change it around to get an intuition or a feel for what turning that knob does to our data. Okay, so we've determined that negative 250 kilometers per second is a decent guess. Now we'll remind ourselves that when it's negative, it's moving towards us. So that means that Andromeda is being blue shifted. Pause for a second and think to yourself, if blue shift is what happens when something is moving towards us, why might Andromeda be blue shifted? If you've guessed that Andromeda is blue shifted because the galaxy is on a collision course with the Milky Way, then you'd be correct. We still are going to have a little bit of motion within the galaxy because the galaxy itself is still rotating. So some of the stars are moving away from us, even as the entire galaxy is moving towards us. So in your own time, you're going to go through and you're going to repeat that for these other stars. Remember, if your template, the black value, does not seem to match the shape of the red value, change what type of star template you're loading up. Okay. So what we're going to then do is take this information we've gleaned. We've seen that probably there's a red shift where the galaxy is moving at 250 kilometers per second towards us. And so what we're going to do is we're going to plot all the velocities of all of the stars that we are seeing in a section of Andromeda. So what I'm doing in this cell is I'm doing something very similar to what we did before. I'm loading up the columns of a text file. I'm unpacking them all, and I'm putting them into these variables here. It isn't super important that you know what these variables are, but we'll go over them briefly. RA and dec, these are right ascension and declination. They're essentially coordinates on the sky. We've seen these if we read through the How to Read a Scientific Article paper. We saw what this looks like. It's a way to plot up our information based on what it would look like on the sky. Xi and eta are also coordinates, are X and Y coordinates that are going to give us position. And F47W and F814W. So cast your mind back to yesterday to that presentation about this properties of stars, and think about that HST, the Hubble Space Telescope band passes. Now, those band passes are areas of the spectrum that the telescope is optimized to cover. And so what we're doing is we're taking the light in one of these sections and in another of these sections. And those sections of wavelength space are labeled this way. I should have pulled up that just so you can see it directly, but you can pull up that presentation and remember these are two different areas of the spectrum that the telescope is covering. We also have our velocity and the error in our velocity. Okay, so this next line is just converting these degrees are coordinates that are in units of degrees to kiloparsecs. Kiloparsecs are a unit of distance like meters that we can picture really easily. And the way we do this is by multiplying these values, both xi and eta, times 13.67. And there are multiple ways to do this. What we're doing here is essentially saying take xi, multiply itself times this value. If you didn't want to do it that fancy way, another way is to write it is xi equals xi times 13.67. We're just redefining our variable. We're saying, yeah, do xi, we're going to still use the name of this variable, but we're just putting it in different units, so we're going to multiply it by this value. So now we know that our xi value is in terms of kiloparsecs. So we're going to use that information, all the stuff we've loaded in from our text file, to make a plot showing the position of the stars in the sky and color coding them based on how fast they are moving. So to break this down, we are making our plot again. We're getting our axes out. Is there something in the chat that's important for me to see?
Yeah, sorry. Hey, Maddie. So there's a question about RA and deck versus chi and eta. What does that mean? And how you're converting between the two?
Between RA and DEC. You know
Yeah.
what? I'll be honest, I'm not an observer. This is not something I'm familiar with or work with a lot. I'll also say it's not that important. So if our folks in the chat want to go ahead and answer that, if they're observers, feel confident about doing that, go ahead.
I can answer that very quickly because I also am not an astronomer, but I just checked. So Ra and Dec are the actual locations for the universal system that astronomers use to reference stars and galaxy in the sky. And Xi and Eta are relative coordinates that don't have a strong where the reference is always moving. So these are just Xi and Eta are arbitrary.
Okay.
Yes.
So
All
think
right.
about it this way. If you looked, oh, go ahead.
Oh, yeah, go. Should I? Yeah,
I
okay.
want to build on that while we're thinking about it. So think about if you looked at the constellation of Orion, which is in one part of the sky, and maybe looked at the Big Dipper in another part of the sky. Those are the names you're familiar with. Those are two constellations that are in very different parts of the sky. They have very different RA and DEC. Those are our sort of X and Y coordinates on the sky. Kind of like longitude and latitude. But if I wanted to zoom in on some part of Orion and just take a picture of it, it's not really helpful to do things in terms of RA and DEC. I want to think about things maybe in terms of like locally, Orion is, has this x-axis and this y-axis. That's going to be our xi and eta.
Yeah, exactly what Maddie said. And I just need to add that the conversion is basically a conversion between angles and distances. So Ariane deck is exactly like Autumn and Maddie described. These are angles. So in case of, say, if you compare it to the globe, to the Earth, it's like latitude and longitude. So these are just angles. And you can basically describe any object in the sky, the position of any object in the sky using these coordinates, R and Z. But in our case, we are converting it into distances, not distance to the target to Andromeda Galaxy, but distances laterally. So we are basically converting what, say, 1 radian or 1 degree of angle would subtend on the sky. And if you look at the plots in later notebooks, it'll become more clear that we are basically plotting the image of the Andromeda Galaxy using distances and kiloparsecs, using the chi and eta coordinates. And the distance becomes relevant because we find the velocity dispersion. But that's for a later notebook. It should become more and more clear as we move along. Over to you, Maddie.
To point out what we're talking about when we think about like how this angular distance is not always actually how big something is. Think about this angle. This angle is the same when we're standing this far away, in which case we would be only this large, if everyone can see my mouse moving. But if something is much further away, it would subtend the same angular distance. However, it would actually be much bigger on the sky. Sorry, it would be the same size on the sky, but it would be much bigger in reality to subtend this entire angle. Okay. To return to what we're doing, the reason we were thinking about converting those is we were wanting to just put things in terms of a familiar variable, which is say kiloparsecs, like how far these stars are in kiloparsecs from the center of Andromeda, or at least the point where we are taking a picture on Andromeda. So to reorient ourselves, we're back to thinking about plotting this up. When I populate a plot, one second. When I populate a plot, I'm going to take this axis variable and we're going to do things like set our y label, set our x label, set the limits we want to plot in, and then we're going to go ahead and actually do a plot, which is the scatter plot in this case. And we're going to put in our x value, our y value, and we're going to colorize it by by the velocity. So with this is actually a really important line right here. This is C. You can also write color, but C is more common. So color is equal to the velocity. And then we're going to choose a color map we want to correspond to the highest velocity and the lowest velocity. You'll see what that looks like in 1 second. S is setting the size of our scatter plot points. And in particular, when we talk about the color map, it needs to have, you don't necessarily need to put these limits in it. Your matplotlib will decide by default based on whatever your highest and your lowest values are, what these limits should be. But we'll see in a second why it's valuable to explicitly set the limits of this color map. Now, without knowing what a color map is, it's not actually that helpful for me to tell you these things. So let's go ahead and see what we're plotting. Okay, this is very tiny. I apologize. I'll zoom in 1 second. But to point out what I was saying, this color map is a way to represent different values based on the color the point is. And as we can see, those limits that we gave it mean that yellow is 100 and dark blue is -700. If I were, for example, to change this to 500, we'd notice that now dark blue means it's -500, but we are actually missing information because we know that there are values that are -700 in here, and we don't know if these dark blue points on our plot now are they -600, -500, -700? We don't know. So it's important to set that range to capture all of our data. Okay, so we have piped out, we've sent our scatter plot information to this. The only reason we do that, and this is just one way to do it, is so that we can use our color bar. So we're putting that in here, we're saying, please make me a color bar for this. And we're making a label for our color bar that tells us what we're plotting in color is the radial velocity. So now I'm going to zoom in a little bit. We can see that what we're plotting is indeed our C and our eta values, which are in kiloparsecs. And so we can see that from, the center of the galaxy at 0, 0 here, we're seeing one arm of Andromeda and a little bit of another arm of Andromeda. And indeed, there is a difference in how these velocities are distributed. Some of them are, in fact, moving towards us, moving away from us, being positive, and quite a bit of them are moving towards us, which is the negative values. But since we learned about the concepts of redshift and blueshift, what we want to think about is, are these stars redshifted relative to the center of Andromeda, or are they blueshifted? And one way to do that is just tap into the human ability to recognize colors. It's seriously something our brains are really, really good at. And it's a really important way to represent scientific data. So we are going to choose a different color map. So this color map is one that goes from yellow to blue. We want to think about redshift and blueshift. So a good color map for that, I think, let's try this one, seismic. This is going to be a red-blue color plot. And we want it so that our things that are blue shifted are going to be in blue, and our things that are red shifted are going to be in red. So that instantly, we can pick out with our eyes which ones are red shifted and blue shifted. So I'm going to run this, and I'm going to tell you right now that it is not going to turn out the way we want it to, and we'll see why in a second. Okay, we've got some red, we've got some blue. So what story is this plot telling us right now? It's telling us the story that all of this in red is red shifted and some of this is blue shifted. Now take a look at our color bar. Remember, blue shift is when it's negative and red shift is when it's positive. Is that what this color bar is doing right now? No. So we need to make it so that 0 is white and then everything above it is red and everything below it is blue. So what we're going to do is we're going to go back to those limits and we're going to artificially pump up our upper limit. We're going to make it match the lower limit, negative 700 and 700, so that where it's white in the middle will be exactly at 0. Alrighty, there's our answer. Really interesting. See, we were lied to before by our color map because we didn't choose the correct colors to correspond to what we wanted to. And look, it is actually telling a really different story. In fact, much more of this is blue shifted than we expected it to be. I mean, there are some in there that are slightly moving towards us. That's because even though Andromeda moving away from us, to articulate again, red is moving away from us. That's because Andromeda as a galaxy is coming towards us on a collision course with the Milky Way, but it is still rotating, and some of that arm is going to be going this direction, even as it is moving towards us. And so, I think this was actually what we were supposed to do. Indeed. You don't have to copy it. It is in fact down here as well. And so I want you all to take a look at this plot and extract what you think an average radial velocity value would be. This is something you can do in your own time, because we are actually going to move on from this and continue to expand our understanding of Andromeda by thinking about rotation. So, we'll take a short break after we go through this next lecture. I see we have a hand raised.
Oh, that was just me, Madeline. I was just going to say we have 10 more minutes left for this notebook.
Awesome. Okay. Let's think about some interesting variables we're able to poke around with. Let's go back and try one more time. We can all do a work along together, which is trying to, actually, what is more interesting? We're going to spend a short period on this notebook, and then we are going to move on because there are some interesting things we can spend some more time in the future notebooks. So we're turning back up. So we got our sort of average, what our velocity should be. We got a good guess for what our velocity was from lining up these spectra to see what the red or blue shift was. So let's try it again. We're going to do this alongside one another. We're going to pick a different star this time. We're going to say, 1757844. And I'm going to start at the beginning again. I'm going to see maybe it's a main sequence star in Andromeda. I load those up. I plot my guess. Oh, very much no. No, that is not the same shape of spectrum. Okay, so it's not a main sequence star. Let's try another guess. RGB star. That error told me that I typed something wrong because it said, I don't find this file. And indeed. G. B. There we are. So to resolve that error, all I had to do was actually type the right name of the file. Okay, is this going to be the same shape? Not especially. So maybe this is also an AGB star. We'll see. AGB. Okay, that's a little closer. Interestingly, probably what this tells us, folks, is that yes, the closest fit seems to be that it is probably an AGB star, but not every AGB star is the same. It'll have some of the same broad spectral features, so we can use this dip to align them. But indeed, not every star is going to look exactly like the template. All stars are unique, just like us. So to zoom in again, what we're zooming in is to this range of spectra. Man, I don't think I can confidently use this stellar spectrum to align it because look, the features when we zoom in are not that close. Maybe we've missed something. Maybe indeed it is a different star. Rather than get into that in depth, we're actually going to look at the other one and hope that it is a more obvious alignment. Okay, we're going to keep that pretending like it's an AGB star. Is that a better fit? Nope, so it's not an AGB star. We're going to go back. We're working with star 491422 again. And we're going to say maybe it's a main sequence star. Is it? No. Look at none of the right peaks. Okay, last check. RGB star, red giant branch star. Is it a red giant branch star? It definitely is. Okay, look at that. That's some nice agreement right there. Visually, it looks like our guess of negative 200 kilometers per second is still pretty good. We won't know until we zoom in again on this range right here, try to see some, or this range right here, to see some of these spectral features in more detail. Let's see. Okay. So looking visually, our alignment's okay. Maybe this one isn't exactly negative 250. Maybe let's try negative 200. Oh, interesting. Okay, so notice that. This is why I said it's helpful to sometimes pump up the numbers to see what happens. So when I made my value smaller, it shifted to the right. So that tells me I actually want to make my value bigger than 250. Let's try 270. Okay, a little closer. I'm going to call that a decent average because these peaks are almost aligned. This peak is dip is almost aligned. This dip is almost aligned. That's not a perfect science because, of course, it won't perfectly match the spectrum because each star is unique. And so, okay, that's actually something interesting. We found that our first star we plotted was about negative 250 to get a good alignment, and this one is negative 270. And so that's why it's interesting and important to go plot all of the stars in the system to see their blue shift and red shift, because we saw that the velocity for two different stars was indeed different. And so that's why the information about finding an average velocity for Andromeda is interesting question. If I had to eyeball this, I'd say, it seems like on average, the colors put it somewhere around 200-ish. So let's take a breather for a second. We'll think about what does it mean again. I already alluded to this. So this galaxy is rotating. That's why some of these stars are moving a little bit away from us, even as Andromeda speeds towards us. And I really want to highlight that velocity information that we're getting is not about how fast Andromeda is moving towards us. I think I misspoke earlier. I think I said that 250 kilometers per second is how fast Andromeda is moving towards us. That is not true. This is the information about how fast it is moving relative to the center of Andromeda itself. I think the information about how fast Andromeda is moving towards us may have already been taken out of this. So what we're seeing here is the rotation of the galaxy. So negative 250 kilometers a second, that's how much fast it's moving relative to the center of the galaxy, moving towards us faster because it is rotating towards us. All right, we're going to go then quickly to this idea of galaxy mergers and rotating galaxies. So I'm going to play a little movie here. I don't know why scientists always say movie when they're talking about a GIF or a video, but it's just something we do. And so what we see in this movie is what we would see if we were able to stand outside all night and stare at the sky. This is, of course, enormously sped up over the course of a night, probably 12 hours or more, as we see the Milky Way moves across the sky. This is due to the rotation of the Earth. We can see a similar thing here with some nice dramatic music. I don't know if the dramatic music comes through, but this is a helpful way to visualize the fact that the Milky Way is not moving. In fact, our Earth is rotating. And what we're seeing is one arm of our spiral galaxy. All right, I hate to cut off the dramatic music, but we are not able to zoom out on our Milky Way. It is simply too vast, and we've never sent a manned or unmanned spacecraft really very far from our own solar system, never mind to get high enough above the Milky Way to be able to take a downward-looking picture of it. But we can know from looking out at other galaxies that we probably, well, we're quite confident we live in a barred spiral Milky Way, a barred spiral galaxy that looks a little something like this. The bar just refers to the fact that it's a little bit flat here in the middle. And importantly, not to scale someone has put in this presentation, our sun lives somewhere out here, about 25,000 light years from the center of our galaxy. And so when we're looking out, we're seeing, one of these arms here. So an important thing to know about a spiral galaxy is, yes, it looks like a hurricane. And so we can tell a lot from our own experiences on Earth that probably this is something that is actually rotating, that it is spiraling like toilet water circling the drain. But importantly, not everything in the spiral galaxy rotates at the same rate. So as you can see in this still image, the indication of these arrows is that indeed the center is moving much more quickly and it rotates than the outsides. To see a GIF of what that looks like, this is a very, very exaggerated example, but it'll look a little something like this. Notice how the stars in the middle are moving, spiraling much faster than our outsides. A fun digression is that indeed we expected this outside rotation to be much, much, much slower than it turned out to be. And it was those observations by Vera Rubin, a woman in the 1980s, that told us, hey, there's actually dark matter probably around these galaxies that are making their outsides move faster than we expected. But there is still a difference. They are still rotating faster in the center than they are on the outsides. And so what does that tell us about the plot we just made? How can we apply that information? So this is the speed at which the heliocentric velocity.
It's a radial velocity.
Okay. So this is the speed at which they're moving relative to us, the arms of Andromeda. Remember, again, our center was somewhere around here. And so some of these are moving towards us at great speed, and some of these are moving I guess, I don't know which frame Raja meant for this, whether they're moving away from us at great speed or moving towards us at less speed. We see the point here, the takeaway from this plot is that there is a difference in how fast these are moving depending on where they are in the arm. Closer to the center, they are moving much more quickly, and farther away from the center of our galaxy, they are moving, or center of Andromeda, they're moving much more slowly, just as we saw in this GIF here. Okay, so what this is a quick video, maybe. Nope. Okay, the video was not playing. Ah, there we are. Okay, so these are computer simulations. The kind of things you are learning to do today can map to these sorts of computer simulations where people are making simulations of how they think galaxies would merge based on the information we've observed. And notice, that's pretty cool that the computer simulation is able to make something that's mimicking a real life picture of two merging galaxies we've seen from observations. And it's fast forwarding in the computer simulation in time to imagining what this merger would actually look like. And oh, look, it actually looks like another merger we've observed on the sky, a different set of merging galaxies. Oh, interesting. In some partway through its merger, when it's past each other and you have these tidal streams dripping out from each other, it actually looks like a different set of merging galaxies we've seen. All right, and as these two come closer together, almost kissing, it makes a beautiful structure that we've also observed in the night sky. And so the idea is that we can use these computer simulations to compare to real life. We're not making computer simulations like this today. These things take hundreds, thousands, if not millions of computer hours to run. And what we're doing today is, though, information that helps make these computer simulations because it gives information about how quickly these galaxies are rotating and also information about, how fast Andromeda is moving towards us because, as we can see in this artist's rendition of the event, though Andromeda is this tiny speck over here, within 2 billion years, as it comes towards us, it's going to start to take up our entire night sky until it begins to merge with the Milky Way, violently ripping the gas from one another as they pass through each other. Our actual stars will not collide because the spaces between stars in the galaxy are so enormous. But the results after 7 billion years of our galaxies merging together will be like a nightly firework display every single night. I'm going to play through this again because it's quite quick and quite spectacular. So that's Andromeda getting closer and closer, closer, until the gravity of Andromeda and the Milky Way begin to pull on each other, and they strip each other's gas and stars away, just like we saw in the last demonstration, last video. And a band of glowing gas and stars. And will probably end up being actually a different shape, a different type of galaxy after this. We will no longer be a spiral galaxy, but will probably be something more like a lumpy blob called an elliptical galaxy. All right. So it's time to pass this along to Artem. We are going to jump into how we're going to use this information to... Oh yeah, I don't remember what the next notebook is. Artem, take it away.
Yeah, thank you, Maddie. And really impressive videos. This is something that I really love about astronomy is how beautiful everything is. And yeah, just to imagine the scale of how long all these things take. And by the way, fun thing about the collision about Andromeda and Milky Way is that a lot of people debate on what is the name of the merged galaxy, Milkdromeda or Andromeda Way. And the funny part is that we have 7 billion years to figure it out. So we do have time to have these debates. All right, so we have finished with notebook 4 and we are switching to notebook 5. So yes, to notebook 5. So you can go back to your home and double click on the simulated disk activity, and we're going to do some simulations. So here's my window that you should be seeing. And so in this notebook, what we're going to do is we are going to make a simulation of a galaxy. So we are going to generate random points, and these points will have meaning. And so let us just go through it. So as usual, we start our notebook by importing all of the useful libraries. So NumPy for doing all the scientific computation with arrays. We're going to use matplotlib to do figures, of course, and we want our figures to be inline, so within our notebook. And then one module that we haven't heard of before, but is called fake disk. And what is this module? This is not a standard Python module. This is actually a script that is in your folder, which is here. And you will notice that this file does not have the extension interactive Python notebook. It has the extension Py, which just means Python script. And you can double click on it and it will open up. And what you see is just a more standard Python script that contains a lot of code. We're not going to go through that code, but what it does is that it defines all the useful properties for the galaxy we are going to simulate. So the purpose here is not to learn how to make that simulation, but how to use that simulation. And this is a very general concept in Python, right? We do not want to reinvent the wheel. We want to use what other people are doing. And so this is what we're doing here. And by the way, essentially, this whole script is when we're importing this inside our cell, it has the exact same function. It could be the same as just executing this whole script as one cell. So imagine all these lines are as just being one giant cell. All right. And so these are all the modules we need, and we run them to import everything. Then the next step, we are going to define a function that is going to make a figure of the galaxies that we're simulating. So as usual, it might be a little bit scary to see big functions like that because they have a lot of different lines and groups of lines, and then there are if conditions, but don't worry, just take your time to go through them and read what is the name of the function, what are the arguments, so what is that we provide as information to a function, and what is happening. So so here I can see that the first step is to create a figure, an empty one. And to this figure, we are going to add some information like X labels. So for the X axis, Y label, we're going to add the title. And then we're going to change the limits that we're going to show for the X axis. And we will see a little bit later why that is relevant. It is sometimes useful to not read linearly. So I'm going to skip this part, the if statement for the moment, and I will focus on the last two lines. And so you will see, do you see that one of the arguments is an object that is a simulation? This is the simulated galaxy that we are going to produce. And the second argument is some quantity that we want to have in the color bar. And so essentially, the most important lines are these two, because this is where we're creating a scatter plot. Remember what was said earlier, a scatter plot, it takes X coordinates and Y coordinates. So here it's there's a letter Z, but this is just a convention. It actually represents the Y position of a galaxy on the figure. And then we use as the color the quantity that we defined earlier. And then for this scatter plot, this plot with a bunch of points, we're going to create a color bar associated with that data. So essentially, this is a function that will show the map as a matplotlib figure, as a scatter plot. And so if I run the cell, just like before, nothing happens because I am simply defining a function and I'm not running anything yet. And make sure that you're running the cells and that you have this little number that shows you that the cell has been executed. All right, so time to make a simulation. Hope you're excited. So the way this specific simulation works, like Maddie showed you in the previous notebook, it is essential to provide inside the function what are the different parameters. And so here is a list of all the parameters and their meaning. So inclination is what is the orientation of the galaxy relative to us. The position angle is how it is rotated in the sky. We're going to play with these parameters to understand them more intuitively. Then, since this is a simulation, we are defining what is the rotation velocity of the stars in the galaxy, the number of points. So here it's the number of stars. And then we have the shape of the rotation curve and scale factor and dispersion. But we're not going to use the shape, and we will keep the other pretty much at the same values. Yeah, but again, I want to emphasize that in a simulation, we are choosing what we are creating, and the goal is for us to see how it would actually look like. All right, so let us define this galaxy that has 10,000 stars. And by the way, in Python, if this doesn't, if you are getting confused about the number of zeros and you want to group them in groups of 3, you can put this underscore. So this is going to be interpreted as spaces, but for numbers. So don't put a space because that will give you an error, but use an underscore if you want to group by groups of 3. All right, so we're going to provide this radial velocity that is in kilometer per second, so the same unit as before. Are 2 angles that determine how the galaxy looks, dispersion and scale factor. And in this line, we're actually running the simulation that is the function fake disk that we imported earlier. And we are appending this simulation inside this variable simulation. So this variable simulation is going to be a very, very big, very complex object that contains all the information. It's a very big object, but don't worry. Things will be very clear when we actually get to use them. So I'm running the cell, and you see that this simulation actually ended pretty fast because we have a small number of points, but we are going to play with that a little bit later. All right, and so one thing so the figure that you saw a little bit before in the presentation that Maddie gave you, there we were looking at the velocity of stars in the Andromeda galaxy relative to us, and you were saying that there was one side that was one shade and other side that was another shade because stars move around the center of the galaxy. And so here, what we're going to do is, for our simulation, we are going to simply represent the X and Y position of every star as defined in our function. And the color of each star is going to be represented by this variable Vy, which simply means the velocity relative to us. And so if I run the cell, this is the result of our simulation. And again, you see that radial velocities that are negative represent stars that are moving away from us, and radial velocities that are positives represent stars that are moving towards us, and that is because the galaxy is moving closer. And so, all right, and at this point, let's just quickly go over the different parameters that we can play on. So for example, I said that there is this variable PA0, that is the position angle. This represents the angle between the axis of the galaxy and the vertical. So for example, if I put 0 for this angle instead of 37 degrees. So by the way, 37.7, this is the angle that corresponds the best to the Andromeda galaxy. But if we put 0, then how does this figure, will this figure look like? Do you have any guesses in the chat? So if we define the position angle to 0, do you have any guesses before I actually run the cell? All right. Yeah, so like I said, it's the angle with the vertical. And so here we see that the galaxy is now oriented along this axis. And if I put that to 45 degrees, then the galaxy is oriented at 45. All right, so I'm going to put back the 37.7 angle, which is the Andromeda galaxy, but feel free to play around with these parameters. And so the inclination, this represents what is the relative. So the galaxy is like a disk, like a frisbee or a plate, and the inclination represents the angle between. So at inclination of 0, you would see the disk face on. You would see it as a circle, and at inclination 90, an inclination of 90 degrees, that will represent the galaxy that you see edge on. So it's so you will see it completely flat. And let's actually check that out. So let's try a very low inclination of 5 degrees, for example, at first. And so this is if we, at a very low angle, we are almost seeing the galaxy face on. And now if I put this at 85 degrees, so very close to a right angle, then we see the galaxy edge on. So we're not changing the shape of the galaxy itself, we're changing how we perceive it from the Earth. All right, I'm putting back the value 77 and rerunning the simulation. All right, so far, so we can measure radial velocities in the galaxy, but some other quantities that are interesting from a scientific point of view, some values that are useful for scientists to analyze, is what is called the dispersion in radial velocity. So I'm going to explain that very briefly. So what is going on is that for each star in the galaxy, so imagine you pick one star, doesn't matter which one. And then imagine you draw a circle, a small circle around that star. And then for every star that is in that small circle, we're going to look at what is the dispersion, so which means what is the typical difference between radial velocities. So you can see that yellow points and dark blue points, they're not like reproducing an exact pattern. They are a little bit scattered around. There is some fuzziness, some randomness. This is because even at the same position in the galaxy, stars can still have different radial velocities. And so what we're trying to do is that for each circle in the galaxy, each small circle in the galaxy, we're going to check out how much there is variability in that circle. All right, so you don't have this cell, by the way, this is something I added. So what you have is this cell. So what we're going to do is we're going to not look at the radial velocity anymore, but we're going to look at the same galaxy, but the color is going to be the dispersion. How much spread, how different are the velocities at any point in the galaxy. And so to do so, we're going to do a dispersion. We're going to define a circle that is 200 arcsecond in radius. And this is just as a reminder, 1 arcsecond is 1 divided by 3060 degrees. This is just a definition, which is that many degrees. And so if we're doing a smoothing over 200 arcseconds, we're actually looking at that many degrees in radius. And so in this cell, the first step is to convert 200 arcseconds into an actual physical distance in parsecs here. And this is achieved, so this has been already done before. So you recognize this variable arcsec to kiloparsec. And here, this is the actual radius for the smoothing, how many stars we're looking in one circle. And so that is 200 times this arcsecond to kiloparsec. And I did create this additional cell where I'm just printing the value of the smoothing circle, which is in parsec. And so if I run the cell, what I see is that I'm smoothing over a circle that is 0.76 parsec wide. And so this is just to give you an idea of how big the circle is when I look at adjacent stars. All right, so once we defined this smoothing circle of how far we're looking, so the actual statistical distribution, the actual information that we are trying to get about the distribution of radial velocities, we are going to store these in these two arrays, in these two NumPy lists, sigma and sigma SV. And so, and these lists, these NumPy arrays, they have the same length as the number of stars, and here it's 10,000 as we defined earlier. And so for each star, we are looking at what is the typical dispersion. We will talk more about what it means a little bit later. We use this function that was already defined in the simulation, so we don't need to define that function to recover this property. So it's not very important to understand how this is obtained. Just keep in mind that we're extracting some additional information from our simulation. And so once we get this dispersion, so once we get this statistical value of what is the spread in velocities around each star, we are using the same function to show the map as before, where we have the same simulation, but this time the color is not the radial velocity, but this new array sigma that corresponds to velocity dispersion. And we already have, and like before, the color maps, they are controlled by parameters Vmin and Vmax, and these values just show that we're going from no dispersion to a max. All right, and so if I run the cell, this has taken like half a second, which is fast, but we are already feeling the effect of doing heavier and heavier computation. And so this is what we get. And so again, this is a map of velocity dispersion, which means at any given point in the galaxy, how different are the velocities of two adjacent stars. And the reason why we called the circle a smoothing circle is because this essentially means that we're smoothing out the information. And so, all right. And at this point, we can, so we see some patchiness, but because we have a small number of stars, we are also missing some parts of the galaxy, so we can actually increase the the number of stars. So let's try with 50,000. So we will have 5 times more stars here. So let's run the show map of the radial velocities alone at first. And here you see what is the effect of having 5 times more stars. So again, all of these stars were chosen at random, and this is how our simulated galaxy looks. And the advantage here is that you can intuitively see by eye the regions where you will have strong dispersion and regions where you will have low dispersion. So if you look at regions where you have a lot of points that are blue and yellow next to each other, that means that there are 2 close stars that are moving at very different speeds. And so that means there is a high dispersion. But then if you look in a region where you only have yellow points and nothing else, then that means that all the stars are moving at the same speed. And so the dispersion is going to be small. And this is what this second figure is telling us. If I run this again, and you see that half a second, but multiplied by 5, this takes a little bit more time. So it shows that even computers have their limits, but it's okay. We can just be patient, wait a few seconds, and here is our map. And so once again, what we're seeing here is this dispersion that I was talking about. And you see that this dispersion is quite patchy. You have like small clouds with slightly yellower regions and small regions with slightly blue regions. And so for scientists, it is very interesting to see how so another parameter you can play around is how big you want the smoothing to happen. And the most extreme case would be what happens if I smooth over the entire galaxy? Do you have any guesses of what will happen if I just like define my circle as being as big as the galaxy? Do you have any guesses? So in order to do that, I have to define like 20,000 arc seconds. Maybe not, maybe actually, let's do 5,000. Okay. So with 5,000 arc seconds, and we have to do it in this cell, actually, this is going to be almost 20 parsecs wide circles. So if I run with this moving circle, so once again, we have 50,000 stars. So take your guesses before the figure appears of what you expect to see. And if the simulation is too slow on your computer, feel free to drop down the number of stars. You can do 20,000 or 30,000. That works perfectly. All right, so this one actually will take a little bit of time because there are more stars. Oh, okay. And very interesting. So you can see that because we smooth over a very, very wide region, we just lose information about very, very small structures in the galaxy, which makes perfect sense because this is what we're doing when we're smoothing out information, right? Anyhow, and I will go back to 200 arc seconds because this is what we want to study. So I'm going to run this cell again. And so one technical point here is that the smaller the circle that you are smoothing around, the faster it will be because you have less stars in a small circle and you have more stars in a big circle, of course. All right. So I'm back to this point where we have structure. And let's say that I'm interested in a small, narrower region around the center. This is why we defined in our function at the very beginning. So if I go back to the very beginning of this notebook, we had this parameter cut out. What this cut out does is that if this parameter is true, we are going to look at only 25% of the figure. So we're going to zoom in 4 times towards the center. So I'm going back to the cell where I have the cutout. And here I have said that I do want the cutout, and I will run that. And this is what we get. And so here we are showing the distribution of radial velocities, but I can change this parameter to be the velocity dispersion. So as a reminder, the velocity dispersion is sigma. So I can simply take that from here and replace that here. And this is what I get. And so just like before, because even 50,000 stars is a pretty small value. So we have, again, some patchiness, so it's not super easy to see structure, but it is possible to zoom in and see what are the velocities of stars around the center of the galaxy. And so there are many more parameters that you can play around with, for example, these how you want the scale to be. So here, oh, all right. Sorry, when doing the previous parameter was minus the highest speed to the highest speed. When we're looking at dispersion, the minimum value is 0. So I actually need to change that to 0. All right. And so here you see all the dispersion of all the galaxies. And actually, yes, I made him. Sorry, yes. The max value is also not the value of the radial velocity, of course, but the max value of sigma, which is my new array. All right. Now we are seeing that, for example, close to the center of the galaxy, if you squint your eyes very hard, you will see a little patch of yellow here, and maybe some smaller ones here, bluish here. And this way you can actually see by eye what is the approximate size of these feature. And again, and by the way, the label is now incorrect. I'm very sorry. So I would need to take this because these are velocity dispersions. So here I just changed the label so of the color bar, so it represents the correct quantity. And now we have everything that is right. And so just to summarize, what we have seen here in this notebook is that we are importing a new module that has been defined by someone else. This is not a standard module that will exist in every Python distribution. This is just a script that we provided ourselves. And this script, it simulates galaxies with some parameters that we have to provide these parameters. And when we created that simulated galaxy, we used our function that shows a map of the galaxy to look at either the radial velocity of the stars. So are they moving towards us or further away from us? And we took a look at the dispersion of velocities, which means for 2 stars that are close to each other, how big is the difference in their velocity. This is what is the dispersion, which is another very useful quantity to characterize galaxies. And lastly, we looked at the velocity dispersion, what happens when we do a cutout near the center. And so below, we have some exercises that maybe in the interest of time, I'm not going to go over, but let's just read what is here. And by the way, these are, so far we have been mostly changing programming cells where we provide instructions to Python. We can also change these markdown cells by clicking twice. And so here, you can actually add your own answers below. So if I read the text here, what I see, so now that we know how to use these simulations and figures, let's see what we can do with that. So if galaxies A and B have the same geometry, so that means the same scale factor, but one galaxy has twice the rotation speed than the galaxy B, then how does the velocity field differ on the major axis or on the minor axis? So the big axis or the small axis of the galaxy, and what happens in between. And so I really encourage you to play around with these parameters, just change them, and then you can answer all of these questions directly inside your notebook. And when you finished modifying the cell, you can just run the cell and it will render the text in a nice way. And yeah. And so, for example, there is one question so I think we have just a little bit of time to wrap up things for this notebook. So we can at least answer this very first question. So what PA, what inclination, velocity, and disk radius makes it easier to study the properties of a galaxy? Do you have any guesses? So let's focus on one parameter at a time. Let's say, how about velocity? Would you say it is easy? What type of velocity do we want to make it easy to study galaxies? I don't know if I have access to the chat.
Yes, everyone has access to the chat.
Right. Well, again, you can just play around, and so I'm going to lower down to 20,000 for the interest of time, simulation time. And so here you notice that the color is pretty much the same, even though we have generated new stars randomly. But this time the color bar is going much further. It is basically going as far as the new data set. So because I defined the new velocity as 500 kilometers per second, then our color bar has changed accordingly. And so let's look at the dispersion again. So this generates this plot again. And you will notice that before we had something that went from 0 to 160, and now we have something that goes almost twice as high. And so what that means is that the velocity dispersion is higher. And if something is bigger, then it's easier to actually see and measure. So it does seem like having a higher velocity will make it easier to study galaxies. And so you can modify the cell, and so high velocity makes it easier to study galaxies because the values of radial velocity and velocity dispersion are higher, so easier to measure. And again, I press Shift-Enter to render the cell. And so again, we're not going to cover all of these in the interest of time, but I really encourage you to, even if you don't answer all the questions, just play around with these galaxies. I feel like this is one of the wonders of programming, is just to try things and see what the outcomes are and build yourself an intuitive approach, get an intuition of how all of this works. All right. So now it is time to switch to the notebook number 6. And so go back to your home menu and you can open your double click on the velocity dispersion activity. And this is where you will get, again, if some things are unclear, feel free to ask them on Slack, and the other wonderful mentors will make sure to answer them. So we're going to be done with simulations here. We are back on the real data, and we are going to use the real data that you produced earlier. So we have a new notebook, so we'll need to import all the useful modules again. So importing NumPy for all of the vectors and huge lists manipulation. And we are going to import the matplotlib for doing figures. Now, just like before, we're going to define a function that has the same name, but it is going to do something a little bit different. So here, just by looking at the input parameters as at the arguments, you can guess that we're going to take the coordinates of stars within the galaxy and some arbitrary quantity related to that, and do something with labels and a file name. And so what we're doing is creating a figure, setting the X label, Y label, and title. And here, just like before, we're creating a scatter plot, so just points here and there using X coordinates and Y coordinates. And each point will have the color defined by this quantity. And so basically we're going to do the same as with the simulation, but now we're doing that on the real data that you worked on earlier today. And so one thing that is new is that, so of course we're creating a color bar, but one new function is this function saveFig, which is actually going to save the figure on your computer. It is no longer going to be just something that shows up in Jupyter Notebook. This is going to be a new file on your computer. And what is fun about that is that then you can have this file and share it and put it in your scientific papers. All right. Sorry. And don't forget to run the cell. That does happen sometimes, is you read the cell and you're like, yes, everything works, but then you forget to actually run it. So yes, make sure that you're running the cell so that the function is defined. Okay. Now, so this will probably be one of the a little bit of a convoluted function to understand, but let's dissect it part by part. Don't hesitate to ask questions if you have. But yeah, so here we're defining another function, and what this function is going to do is basically it is going to provide us the measurement of the dispersion. So remember that before I told you we're not going to investigate how to get this. Now it is actually time to understand a little bit more in detail how do we get these fluctuations in the velocities? This is what we're looking for. So here the arguments are the positions of the galaxies, X and Z, and of course, the velocity of each galaxy. And then, like before, we have a circle size, which has basically the same meaning as the smoothing circle that we used in the notebook before. And the quantity we're interested in is to get for every given star, we want to look at how dispersed are the velocities around that star. So dispersion is a list that we're going to initialize with as many zeros as there are stars. And the goal is to compute the dispersion for around each star. And so to do so, we're just simply going to go through each star in our catalog, and we're going to recover its X position and its Z position. And let's understand why by creating a new cell and quickly going over how do we. So this will happen in 2 steps: filtering out neighbors and then actually computing the dispersion. So how do we get the neighbors? So I'm going to create a markdown cell for some to do some math. So imagine you want to compute the distance between 2 stars by Pythagoras theorem. So you don't need to copy that, but you will have this, of course. So from the Pythagoras theorem that the distance between 2 points of coordinates x and z, 1 c2, can be computed using this formula. Let's see. I'm pretty sure I'm missing something. Right, this is LaTeX. Oh, right. Markdown. I haven't used LaTeX in a while. Why is this? Inline? Okay, so I'm just going to show that in comments in the code. So the distance between the one star that is the star number 1 and the star number 2 is going to be the square root of the difference between its x coordinates and the difference between the z coordinates. And now remember that, and so what we want to do if we want to filter through all the stars is we want to compute that difference, that distance between our given star 1 and all the other stars. And because we're using NumPy arrays, what we can do, the distance between one star and everything else is going to be simply something like this. Sorry. So we're using the square root function in NumPy. So the star number 1 is still the star number 1, but then we can directly use the NumPy array X and the NumPy arrays Z that are going to represent all the coordinates of all the stars in the galaxy. And I'm just going to correct everything to have the proper syntax so that this is actually working code. So just again, very simple. If I want the distance between 2 galaxies, I just compute this quantity, these differences with square and square roots. And if I want all of the distance at once, I don't need to make a loop. I can compute this quantity directly. And so these are going to be all the distances between our given star with the integer I and every other star. And so I will start from writing that statement from inside out. So we have this x minus x. So these are all these differences along the x coordinates that are squared. We have this z minus all the z's with which is also squared, and everything is inside the square root function. And remember that Python doesn't care about spaces between elements, so feel free to make it as spacious as possible so it is readable. Now, another function that we have seen that you have seen earlier is how to create masks to filter out different portions of your data. And this is achieved with comparison symbols. And so what we want to create is a list where all the distances are smaller than our circle size here. So what it is going to create is it is going to create an array that contains true, true, false, false, true, false, true, false array saying basically, is this condition true or is this condition false? And once we have this mask, what we need to do is to compute the dispersion. So are we simply looking at and so if we do use this syntax, this is something we have seen earlier. So here we have provided, in the input of the function, we have provided this array v that corresponds to velocities. And here what I'm doing is I'm only keeping the velocities that are at distances smaller than the circle size. So I no longer have a list with the 10,000 stars or 20,000 stars. I only have a subset of these that are closer than this. And why do we? And so the very last step to have this function ready is that we do not want to have the list of all the stars. We do not want to have their velocities. What we want is to know within that circle how different are the velocities. And this is a quantity that we can obtain using the function that is called standard deviation. So the standard deviation function, this is something that you may have seen in spreadsheets or Excel spreadsheet or Google spreadsheet. It is quite a common function in math. And this represents the typical spread of values, the typical basically what is the range between the max and the min, sort of. Yes, and so if you didn't manage to follow all the math, that is totally okay. Just remember that all this function is basically the definition of what we did in the Jupyter Notebook 5. And so it's going to compute the exact same quantity, the velocity dispersion around every star, because we have run this loop over every star, and then we return this array. So basically, we just did the math for something that we didn't define earlier. Right, and this is also just a function. So if I run this cell, nothing is going to happen. All right, and so now the exciting part, because we're not using simulated data, we're using actual data, we're using your data that you generated today to make velocity dispersion maps and to do actual science. So the very first step, so we already covered, so the very first step is to load the catalog. We're in the simulation, all the stars were generated randomly with some parameters. Now we're reading the catalogs. So, and here we are using the NumPy low-text function. So this is the file for the main sequence stars catalog. And these parameters were already covered. So which columns we're interested in. And we're interested in the coordinate psi and eta, and also the velocity of each star, of course. And we have this option unpack equals true. That is important when we are extracting data column by column. And so now there is just one tiny detail about this catalog, is that there was a bug, and to get rid of the bug, we only need to keep all the stars that have radial velocities smaller than 1,000 kilometers per second. So I'm not sure about what is the origin of the bug, but we can get rid of that bug by removing all the stars that are and that have radial velocities higher or equal to 1,000 kilometers per second. And so just like before, the procedure is very simple. We're creating this mask that we are calling keep, which is just a list of all of the points where the absolute value of the velocity, so velocity but removing the sign, is smaller than 1,000. And then we reassign coordinates psi, coordinates eta, and the velocities v by only keeping a subsample of that data. Right. And so now what we want to do is to calculate the actual dispersion map of that catalog. So here, what I'm doing is using the get dispersion function. So I'm providing the data from the catalog inside this function. And this will return the dispersion for each star. And the next line that is here is going to make the figure to show what is the dispersion as a function of coordinate psi and eta. And you will notice that here we provide the label, and here we provide the location where we're going to save that figure. And so just like before, double point means that we're moving one folder up. So we're actually going one folder before upper, where you have all your codes. And then from that point, we're entering the plots folder. And in that plot folder, we are creating this figure. And so one tiny comment is that you notice we have the extension PNG here. And something magical about matplotlib is that matplotlib is actually recognizing this extension and creates the figure in the format PNG. But you can replace that with other formats like JPEG or PDF, and that works as well. So this is because the matplotlib module was designed very efficiently. All right, so let's give it a try. We're loading our catalog. We're fixing a bug by removing some galaxies. We're computing the dispersion just like before, and we're showing that. And this is what we get. So yeah, previously we had the map of actual velocities. Are they coming closer to us? Are they coming going further away? Now what we're seeing is actually clusters where small dispersion means that the galaxy are having the same speed relative to each other. They're going in the same direction with the same speed. And when we have higher values of dispersion, something that is more yellowy, that means that the stars are going in very different directions or with very different speeds. This is how we read that figure. And so these are the dispersions for the main sequence catalog. And so the next step is to do the same for the asymptotic giant branch. And we will do the same for the red giant branch, so HB and RGB. And so to do so, we're going to do the favorite task of any programmer is copy paste, because that works just extremely well. So let's take all of that code as the basis for next steps and just modify everything accordingly. So now, instead of using the MS catalog, we're using the AGB catalog. And we want to make sure that we're changing everything so that we don't accidentally overwrite any useful value that we did before. And so here, MS sigma, this stands for main sequence sigma. So we are also going to change that to AGB sigma. And in the generated velocity map, we need to change this as well. And when we are saving the file, we're also going to save it to a different file. We do not want to overwrite the previous file. You will notice, however, that since we're using the same variables psi, eta, and v in this cell and in the cell before, that means that these values will be overwritten. And so if I run this cell, this is what we get. So it is already interesting to see that we have the same spread in velocity dispersions, but this figure looks wildly different. Not only the colors are completely changed, but the pattern is completely different. And we will see a little bit later how that affects everything. And by the way, I mentioned that this figure is saved. So right now, you can go into your file navigator, whatever the system you're using, and you can see for yourself that if you go back one folder from where your programs are and you enter the plots folder, you will find these two images in PNG format for the main sequence and the asymptotic giant branch stars. All right. Now let's move on to the RGB stars. So at this point, I think you get the gist. And we are doing the same procedure, but this time using the RGB catalog, the same catalog that you created a little while ago. And we make sure that we are applying the filter. We make sure that we change all the variable names that are relevant for us. And don't forget to change the name of the figure where we want the figure to be saved. And so when we run this cell, again, we have the, now we're seeing all the red giant stars that are in the Andromeda galaxy. And so again, you can scroll up and down to visually compare these different distributions. And I think it's really interesting to see that you are the ones who sorted these stars and you sorted them by color. So you said these are redder, these are bluer, these are older or younger. And now you are visually seeing in terms of distance where these stars are located in the galaxy. And you can already make some inferences about what are the properties. So for example, what is the highest velocity dispersion? What is the lowest velocity dispersion? And what is the average one? And so this is why we have this value. So for example, it does seem like the RGB stars have the highest dispersion on average. let's actually check that. So we had this, so I'm scrolling back to the main sequence plot, and we had this print statement. So we're going to uncomment that. We're going to add parentheses. And what we're going to do is we are going to look at the minimum value of these dispersions, the maximum values, and the average value. And so when I run the line, so it has pushed my window back, so you need to scroll back up. And so the dispersions are going from 32 to 140 and are 65 on average. Okay, that's interesting. Is that different from the other catalogs? And so let's do the same for the AGBs. Let's uncomment this line, add the parentheses, make sure that you're adding the right, entering the correct argument inside the min, max, and mean functions. And so when I run this cell, this is what I get. So the lowest is pretty much the same. The highest is also very close, but the average value is much, much higher. We had 65 before, and now we have 95. And so just doing quickly for the RGB catalog. Oops, sorry, I pressed enter instead of shift enter. Right, sorry, it's here. And so now we have, again, so now we have different values for the smallest dispersion, higher value for highest, and we have the highest average value of dispersion. So it seems like we're quantitatively proving that indeed there is a difference in these dispersions between the different populations of stars. And so yeah, this is related to the following questions. What are the observations we can make? The differences that we can say about these figures, what is the same, what is not, what is common. And so we did show that they have different average values. So so that is one property that is different for each catalog. So now, but can we say more about that? And the answer, of course, is yes. And so for that, we're going to use histograms. So a histogram, some of you may already know what a histogram is, but basically a histogram is a type of figure when we look at how frequent each value is. And this is a type of figure that you may have seen in the grading context when you look at the distribution of grades in a class, and you're seeing how many people got an A+, how many people got an A, how many people got a B+ or B-, and so on and so forth. And a histogram is exactly that. We're going to count how many stars have a velocity dispersion between 40 and 60, how many stars have a dispersion between 60 and 80, and so on and so forth. And so in the interest of time, I do have the actual code to generate these. And we're going to start with, just like before, we're creating a figure with this function plt.axis, which are going to create the region for our plot to put information on it. And the function in the matplotlib library to make a histogram is hist. And once we do that, the only argument we need to provide is all of the dispersions for each for one of the catalogs. And what the histogram function is going to do, it is going to count how many stars there are in each bar. And speaking of bars, this is the number of bars is actually provided by this argument that is called bins. And for the moment, I'm going to remove this function. This is actually, I will comment this one a little bit later. And we can also provide a range of for the histogram, how far we need to go on the x-axis. And there are many options that we can play around, such as the transparency level, the color of the histogram, and z order is another parameter for visual purposes that I will mention a little bit later. And so when we run that, this is what we get. So again, remember that this is a frequency plot. We are looking at how frequently do we encounter stars that have a dispersion between this value and this value, or how often do we find stars with this dispersion. And so in this plot, you can sort of see by eye that when we had an average value of 50, around 50, or was it 65, we're basically looking at the center of this distribution. But now we see this distribution as a whole. And just like before, feel free to play around with the parameters. What happens if we use less bins, or what happens if we use more bins? The plot is more or less detailed. But yeah, let's keep it at 30. 30 is a good value, and we will see later on. And for the sake of visibility, I will also add this parameter, edge color, just so we can see a little bit better the edge of these plots. All right, so this is one figure. So this is for the main sequence star dispersions. How do other dispersion look? Well, let's do the favorite activity of a programmer once again. Copy paste that line, and let's just change the quantity that we're plotting. Let's do A, G, and B. And because we want things to be comparable, we will keep the same parameters, except, of course, the color, since for the asymptotic stars, let's use the color green, for example. Now, what is going to happen here is that we're going to add the distribution of asymptotic stars. And again, we're confirming visually what we found earlier, is that the average is now higher. But now, instead of just looking at the minimum and maximum value and the average, we actually see the entire distribution. All right, and all that is left to do is to add the RGB catalog. And also, since we have more than one figure, we're going to need to add some labels to know who is who. And that is just like in the scatter plot. We provide the we specify it with the option labels. So sorry, this is not RGB, this is main sequence. Then this one is for RGB. Oh, sorry, AGB, the asymptotic one, and the red giant one for the last. Oh, and also remember to change the color for the RGB histogram. If you didn't, that is perfectly fine. Let's actually try that out. If we do forget to change that, we will see that we have two histograms that are shown in red, and this is hard to read, of course. So we do actually want to have different colors so we can differentiate them. All right, and so at this point, we're done with the information that is on the plot, but you will notice that we don't understand much because the axes are not defined. So let's quickly do that. So for that, we use, just like before, X label. So this is velocity dispersion in kilometer per second. We specify the Y label, which is a frequency. Then I'm going to, and that is basically it. You will also notice that the label are not shown on this figure because we actually need to tell Python explicitly to show the legend. And when we add these 3 lines of code, this is what we have. So we have the legend and we have the plots, the labels. All right. So I promised to touch a word about this weird parameter, density equals true. This is just a normalization factor. And this tells the histogram to multiply everything by a scaling factor. And basically, when we say density equals true, the Y values are to be interpreted as probability. So what is the probability of having a star at 50 kilometers per second within the catalog? What I can do if I turn this to false is that this will actually show the count of stars. And so now what I'm seeing is that, for example, if I ask the question how many RGB stars there are that have a velocity dispersion of 100 kilometers per second, there are more than 1,000 of such stars. How many stars with 50 kilometer in the main sequence catalog? Just above 300. So this parameter density equals true is just here to tell us, are we counting the galaxies, the stars, or are we interpreting these are probabilities, something that is normalized? All right. And so there is this last step where we want to compute the median or the mean velocity dispersion for the 3 age groups. This is something we have done, but if you want to give it a try and send in the chat what these values are, I'll be happy to take any guesses. So for these 3 populations, how do you compute the mean value of their ages? And also, don't hesitate to add some formatting to your result, not just the numerical value, but a sentence. And if you provide it in the chat, I can actually copy paste it in my code. So I think we're good enough on time for today.
Yes, we've about 10 more minutes.
All right. Well, this is a very last cell, so because we will leave you the interpretation. We will comment that verbally, of course, but yeah. So if you have any suggestions, feel free to drop them on Slack and I can make some suggestions. So we're using the print statement, and inside the print statement, we want to add some text that will say what value, what number we are showing, and then how to format that. And of course, if you have any questions about anything that we covered in notebooks, CX5, and everything else, feel free to post them on Slack. All right, I'm going to start with just the basis for the print statement, and I'm going to add a bunch of spaces so we can have room to play around. So let's see. If we start with the median, MS catalog. So there are multiple ways of doing that. Earlier, Maddie showed one way of printing values, formatted values using format specifiers. I'm more of a F-string fan. And the way I would do that is whenever you have a string of text, you add a little letter F before that, and that allows you to add variables with format options inside of your string of text. And the way to add variables is to use curly braces. So median velocity dispersion for the MS catalog in kilometer per second. And so the actual value of the dispersion, we can obtain it using the NumPy median function. And remember that the MS catalog, the dispersion was actually stored in this MS sigma array. And in order to specify the format, we need to add a colon and say how many numbers we want after the decimal point. So this is how it is read. This is the variable that we are printing. We're printing the median value of all the dispersions, and we're showing that with 2 digits after the decimal point. Don't forget the decimal point, it's very important here. All right, and so if I run this, I finally have this value with this formatted string. And so all we need to do is to copy paste that and do the same for the other 2 catalogs, and AGB and RGB. And here are the 3 values. So we indeed have 3 distributions, 3 catalogs with very different velocity distributions. And here is how we can present the results conveniently. And do your median, so does that look compatible with what we have observed? Again, you can answer in the chat. So do these values correspond to what we see in the histogram for the different median velocities? Yeah, thank you. Everything is consistent. And so the next step of that procedure is to put this result in a scientific paper and send that for the peer reviewing process. So this is it for notebook number 6. Congratulations, everyone.
Fantastic. Thank you so much, Artem, for taking us through these last few notebooks. I'm really excited to see the engagement that we were getting in the Slack channel. So please, if you hadn't had a chance to actually download and install Anaconda, and you were watching and taking notes throughout the presentations by Geronimo and Maddie and Artem and Parajito yesterday, then once you do get that installed and you run things and you have questions, please come back and add your questions into the chat. And so I'm just going to drop that link in here one more time. So this is the Slack channel, and your questions stay there. It also allows for anyone to add their comments and questions to you as well. So please check that out. I will be, I'll download this recording today. Once it's finished, I'll edit it really quickly, upload it to the to our YouTube channel, and then I will send an email like I did yesterday with the link to the recording along with links to the slides that were used today. I'll also include another link to the Slack channel just to reinforce how important it is for you to engage with these fantastic mentors there. I'd like to thank all of you for joining us, and we do hope to see you in our tutorial series next year. In the meantime, Artem, Madeline, Apargito, and Geronimo, you have been amazing, and we appreciate your time and expertise. And as you can see in the chat, we're getting lots of appreciation for you. Thank you so very much.